Hey guys, welcome to a new video in this deep learning and neural networks tutorial. In this video we're going to talk about artificial neural network and specifically layers and activation functions in neural networks. So let's jump into the first slide here where I'm going to give you an overview over what an artificial neural network is. So we have in an artificial neural network we have these different kind of neurons here in the layers. And when we're talking about artificial neural networks, we're operating with numerical data. So like the data that gets passed through this network here is numerical data, and that's why it's an artificial neural network. In later videos, we're going to talk about some other different kind of neural networks where we're going to talk about convolutional neural networks, and there's also some other different kind of like recurrent neural networks and stuff like that. But in this video, we're talking about artificial neural networks. So we have this numerical data here where we have these different kind of neurons in our neural network. So we can see here that we have our input layer here where we have 3 neurons in our input layer. And then we have one hidden layer in this example here in this neural network here. So we could have multiple or like an arbitrary number of hidden layers inside of our neural network. And we could have like several like tens and hundreds of different kind of like hidden layers inside of our neural network. And then at the end here we have our output layer. So we have these different kind of input nodes here which has like each node here has like a value in our neural network, and then each of the connections between our neurons here they have a weight, and then the value here of the first node or like the neuron here in our first hidden layer will be the sum of all the weights here that comes into this node here. So it will be the sum of all these weights coming from the 3 neurons here in the input layer, and then we also have some bias that comes into like the value that we pass to the activation function. But we'll talk about more about biases and stuff like that in later videos. But then the data or like the numbers that comes into to this neuron here in the first hidden layer, we will sum all the weights in the layer here, and then we will give it a bias. And then that value will be input to an activation function where the output from the activation function will be the new neuron value here that we can now pass further in a neural network to the next hidden layer or to the output layer in this example here. So like the process or like the method that we're using here when we're passing data through our neural network is called feed forward. So we have some input values here that gets fed to our neural network, and then we feed those values or the information forward in a neural network. And we can also have feeding backwards where we're doing back propagation. So it is when we're learning or like training our neural network. We're going to talk about that in later videos with back propagation. So the idea here in neural networks is that we feed forward the data from the input layer through the different kind of hidden layers and then to the output layer. And then when we're done with that process, we then take the output, see like how good is the output compared to the input, and then we use back propagation to back propagate in our neural network, update the weights, and then train our neural network in that way. But we're going more in depth with the training process and how a neural network actually learns in later videos. So remember to hit the subscribe button and also like this video and hit the bell notification so you'll get a notification when I upload a new video in this deep learning tutorial here. So in this video here, we're going to talk about activation functions as well, where we have different kind of activation functions, and we can pass an activation function to each layer or like each layer in our neural network, and then those activation function here is like actually like determining the values of the neurons in the neural network and which neuron should be firing and which should not. So we're going to talk about more about that in this video here as well. So first of all here, let's go more specifically into the layers in a neural network. So we know that we have a lot of different kind of types of layers that we can have in a neural network. So the ones we're mostly going to operate with is dense layers in this tutorial here, where we're talking about artificial neural networks. And then later on, we're going to have convolutional neural networks. We're going to use more of convolutional layers and also like some pooling layers, where in convolutional layers, we often have convolutional layers followed by a pooling layer. But we talk more about that in the upcoming videos when we're talking about convolutional neural networks. So in the artificial neural network here, we're often just using the dense layer, which is the same as a fully connected layer. So we can see here we have an example of a deep feed forward neural network, which is a dense, which consists of dense layers. So we can see that each neuron here is connected to all the previous nodes in the previous layer. So we can see that this node here, this node here is connected to this neuron here, and this neuron here is connected to this one up here, and the third one here is also connected to that. So all the neurons has a connection between each other from the previous layers to the layer that we're in now. So that is why it's a dense layer, or as we also call it, a fully connected layer. Then we have some different kind of convolutional layers where we're operating with images instead of numerical data. So we have some different kind of like convolutional layers and also pooling layers. And then at the example over here to the right, we have a deep convolutional neural network where we have some different kind of like kernel layers or like pooling layers, and then we have the convolutional layers, and then at the end of the convolutional layers in our convolutional network, we have some fully connected layers that can actually like give an output or do some classification of the input that we fed to the neural network. We can also have like a generative adversarial network, which is a GAN network. This is just another type of a neural network, and also the recurrent neural network, which consists of recurrent layers. So there's a lot of different kind of layers for the type of neural network that you're going to deal with. So we'll go more in depth with all of these things here when we're talking about this specific neural network in this tutorial. So the main thing here that we're going to operate with is the dense layers, which is fully connected layers, and then in the convolutional neural networks layer, we're having convolutional layers and pooling layers. So we're going to talk more about that in future videos. So now we're going to talk about activation functions in neural networks. So we already know that we have this activation function for each neuron in our neural network. So we have some input here that comes from all the previous nodes. So if you have a fully connected layer or a dense layer, we have the sum of all the previous like nodes. Like we have all the neurons which get multiplied with the weight of that neuron, and those values will all be added together, and then that will be the input to our activation function from the given neuron that we're in now. And then we pass it to some activation functions which will result in an output, and then that output will be the new value for a neuron that we're currently in. So we can see the formula down here where we have some value for a previous neuron, and then we have a weight for each connection between the neuron and the neuron that we're operating with now. And then we sum all of these values here together, as we can also see down over here, we have this x value, which is the value of the neuron, and then we multiply by the weight of the neuron here, and then we sum it all and add it to a bias. So we're going to talk more about this bias here in some upcoming videos and later videos as well, because we can use the bias here to like try to modify the different kind of like activation in the neural network and which neuron should be firing and which neuron should not. So we can use that for some other different kind of things, and we're going to talk about that. So this value here will now be fed to our activation function, and that activation function will give us an output, and that will be the new value of our neuron. So how does activation functions affect the neurons in a neural network? So activation functions, they do nonlinear transformations to the input, which makes it capable to learn and also like perform more complex tasks. So this is one of the most essential things in neural networks is the actual like activation functions, because the activation functions do these nonlinear transformations. And if we just did linear transformations, we could use some other different kind of machine learning methods where we just have some linear regression or stuff like that. So it makes the neural network able to work with videos, audio, and speech, and a lot of other different kind of stuff, because we have this complex task that can be done from doing these nonlinear transformations with the activation functions. So we're going to have some linear activation functions where the output is proportional to the input, but we don't really like use linear activation functions in neural networks, because when we backpropagate in the gradient will be the same, because when we take the derivative of a linear function, it will be constant, and then we can't use that to train our neural network. So it will not work to use linear activation functions in our neural network, and it will just be a linear regression. So we can also have these nonlinear activation functions, which is the main thing that we're going to focus on in this tutorial, because it's the most used ones, and they're just really good because it makes it easier for the model to generalize or adapt to like the diversity of the data, and to also like to differentiate between the outputs in the neural network. And also the nonlinear activation functions, they're used to backpropagate and update the weights during training, as I also talked about, because when we take the gradient of the values from the nonlinear activation function, they will now differ, because and then we take when we backpropagate in our neural network, we take the partial derivative of the weight with respect to the loss or like the partial derivatives of the loss with respect to the weight that we're currently in now, and then we update the weights during training by just back propagating in a neural network. So we're going to cover back propagation and how that is done in later videos as well. So remember to subscribe so you know when I upload a new video, and we're going to like cover all the basic and all the fundamentals of neural networks, and we're also going to create our own neural networks, train them, and also do predictions with them. So activation functions here, they should be differential and monotonic. So we already know why it should be differential, so we can update it during training. So it makes the back propagation possible, which update the weights and the biases during training, as I already said. So it should also be monotonic, which means that we can see down here that it shouldn't change in the direction when it just goes. So we can see that these two here are like a monotonically increasing function, and here we have a decreasing function, and it doesn't change here in the y-axis. Like the sign doesn't change at any time, as over here to the right. We can see that this function here is not monotonic, because we can see that it has this like curve here where it just goes up and then it goes down. And then when we have a differential and monotonic activation function, you can actually like just create your own activation function, but you should definitely use the ones that are already created and already tested, and just give the best results. So the last thing here is that we're going to take a look at the different different types of activation functions that we can use. So one of the most used ones is actually like the Rayleigh function. But first of all, let's cover the linear function, where if we have a linear function here, the output will just be the same as the input, because they will be proportional to each other. We can also have the sigmoid function here, where we have the values here going from 0 to 1, and then we have this function here. So if we give it an x value of, for example, like around 0, then it will yield like 0.5 as a result and an output. So the sigma function, there are some different kind of consequences and like disadvantages and also advantages for all of these activation functions here. So the sigma function can cause vanishing gradient problems, and we're going to talk about what that is in later videos as well. And the output is not zero-centered, which makes the optimization harder when we do that in the training process. So the most used ones when we're talking about like neural networks is the Rayleigh activation function. So we can see here that the Rayleigh activation function, if the x value is less than 0, then we'll just cut it off and it will now be 0. Or else it will just be the same value as the input, like the output will be the same value as the input. Unless it's less than 0, then it will just be 0. So in Rayleigh, not all the neurons are activated at the same time, which can be good, and also like why the Rayleigh function is often used. And it's very efficient and also easy for computation to use this Rayleigh function here, because it's just the same as the input unless it's less than 0. And the output, and one of the disadvantages is that the output is still not sent to 0, and dead neurons, if the gradient hits 0 when back propagating, then it will cause a dead neuron. But there are some different kind of things that we can do to like try to optimize that with some other different kind of activation functions if we have dead neurons in a neural network. So another function here is the tan h, which kind of looks like the sigmoid here, but it goes from -1 to +1. And the output is zero-centered, so the optimization is easier, which is kind of like the thing why you should choose the tan h, but it's not really used that often. And we also have this vanishing gradient problem, which can saturate and also kill the gradients when we're using this activation function. So the last slide here is when to use the activation function, or like which activation function to use, because it really depends on your application and also what type of neural network that you want to create. And I'm going to show you in code here after like how we can create a neural network, add the layers with Keras in actual code, and then how we can specify the activation function that we want to have in that layer in our neural network. So just to summarize here and to talk about like which activation function to use and when. So Rayleigh is the most used one because it just gives better results in general. And in case of dead neurons, with Rayleigh, we can either use like the leaky Rayleigh or the ELU. That can be used to try to solve this problem here with the dead neurons. And I have a graph over here to the right which compares the Rayleigh and the leaky Rayleigh and the ELU. So we can see that we have this Rayleigh here, we just cut it off if it's less than 0, and then it will just be 0. Where in the leaky Rayleigh here, we can see that we still have some values, we can still have negative values if our input value is less than 0, and also for the ELU here. So like they're kind of the same, but there's still some differences, and you should try them both out if you have some dead neurons in your neural network while training. And if not, you can just use the original Rayleigh function, which just gives really good results. So the sigmoid function works good for if you're doing, for example, classification problems. So you could do some classification problems where you're using the ReLU function in some of the layers, and then the sigmoid function when you're going to do your actual like classification in your neural network. And then the sigmoid and the tangent is often avoided because it just causes this vanishing gradient problem, which is kind of hard to solve and also like try to optimize. And tanh is avoided most of the time because it just results in dead neurons a lot of times, and there's other different kind of activation functions that are just better. So we're not jumping into the code here, and I'm going to show you the different kind of things that we have just learned. So first of all, we're going to import from the Keras model, we're going to import the sequential here, so we can create a sequential model and like try to like create the architecture of a neural network. And then we're also going to import from the layers, we're going to import the dense layer and also the activation functions that we just talked about in the slides as well. So now I'm going to show you like how we can create a sequential model, which is the architecture of a neural network. So with Keras here, we can just specify a model here, which is equal to a sequential model. And then inside of this sequential model here, we have a list of all the layers that we want to specify. So first of all, in our layer or in our sequential model here, in a neural network, we have the input layer, which is a dense layer here with 4 neurons. And then the input shape here is like the shape or the dimensions of our input. So in this case here, we just have numerical data in our artificial neural networks. So the input shape here will just be 1 because we're operating with numerical data. If we have like, for example, some images or we have convolutional neural layers, then we'll have some other input shape with this dimension of the image. So in the first layer here, or like the input layer, we specify the activation function here to be ReLU, which just means that the values or like the output will be the same as the input unless unless the value is less than 0, and then if it's less than 0, it will just be 0. So the first hidden layer and only hidden layer in this sequential model here is this dense layer here, which has 3 neurons, and we also specified the activation function to be ReLU in this example here. So this is just an example and like a way to, I just want to show you like how we can create a sequential model, and then in later videos we're going to actually like create a sequential model, train it on some data, and then do some predictions with that model afterwards. So in the output layer here, we have a dense layer which has 2 neurons. So we're going to have an output with 2 neurons. So we can like, for example, do some classification where one of the neurons is one class and the other neuron is another class. And then we specify this activation function here to be softmax, which is kind of like the sigmoid activation functions that we just talked about. But the softmax is really good for when we're doing classifications problem, and is often used when the output should be like some different kind, like some kind of classification problem, which is the kind of like case I want to show you here. So when we have a classification output, we will either have like, we will probably like have a probability of like how certain is our neural network that the first class here is the like the actual like value that we're going to predict, and also a probability of the second class. So we have these different kind of outputs here, which is just like, it just tells us which class the neural network has predicted that the input to the neural network was. So when we create our model here, we can just run the code here. I'll just start with the first cells up here, as I showed you in the previous video. So first of all, we import the TensorFlow, and we also specify that we want to use the GPU of the Google Code up here. And then we can import these sequential models and the dense and activation functions from the Keras layers API here. And then we're going to actually like create our model here with hitting Shift Enter. And now it will create our model, and we will store the model in this model variable. And then we can call this function here summary, and then we can get a summary of our model. So if I run the program here, we will get the same output here, but now we have a summary over like the architecture and the model that we have just created. So it's really good to check that we have created a function or like the neural network as we want to. So we can see here we have 3 layers, where first of all we have a dense layer at the input layer with 4 neurons, and we have 3 neurons in the hidden layer, and then the output layer is 2 neurons. And then we can see over here the number of parameters that we can actually like tune, and also like the trainable parameter in our neural network. So all of these are like the weights and also the values for our neurons in the neural network, as I talked about in the video as well. So we can also create, there's also another way to create a sequential model with Keras, where first of all we can just have like the model 2 here, which is equal to sequential. and then we can use this add function here to add a layer or like add a new layer to our model. So this is actually just the same as we just went over up here, but here we just had this list here of all the layers, where down here we just add each layer individual to the model. So it's all the same layers here, it's just another way to like create a sequential model. And some prefer the first one, and some prefer this one here, where you can go into the model and create a new layer or add a new layer. So we can do the same thing here if we run this model and we do a summary of this model 2 here, and it will result, it will output the same result here, where we have the same number of training parameters, and it will also have the same architecture. So this is how we can create a model in Keras, and it's actually like really easy to create a model here if you just import the different kind of things that we need from Keras, and then we can create this sequential model here, specify different kind of layers, how many neurons we want in our layers, the input shapes, how many output neurons do we need to do for our classification problem, is that was what we wanted to do, and then we also need to specify the activation function we want to do or want to use for each layer in our neural network. So that's pretty much it for this video, guys. Remember to hit the subscribe button and bell notification under the video, and also like this video if you like the content and you want more in the future, because it really helps me and the YouTube channel out in a massive way, and I just really appreciate your support and that you're watching these videos. I'm currently also doing computer vision tutorial in OpenCV with C++, and also an algorithm data structure tutorial in C++. So if you're interested in one of those tutorials, I'll link to one of them up here, or else I'll just see you in the next video, guys. Bye for now.